So yes, you know me earlier. So I think Python was the yes. All right. So no introduction needed. I was thinking how to introduce myself. So all right. So today we're going to talk about principal component analysis. So I believe earlier you have had a class on unsupervised learning and have learned about clustering, right? So why do we need unsupervised learning? So I'm going to ask a lot of questions in the class because you've already done it. Right? So why do we need unsupervised learning? All right, so I think you guys know, but I need to, or what is that? You don't have, I mean, what is the problem in labeling the data? Sorry?
We don't know what is information hidden in that data.
But we can label it, like, we know there's an elephant in the picture. We can say there's an elephant. I mean, in unsupervised learning, but why? Okay, so the question is, why it learns unsupervised learning at all? What is the need for it?
Real data is raw data, you don't know.
Because we don't have complete understanding of the real levels and all that. We might know, but
we might not know. Okay, yes, I mean, that could be. First thing is, I mean, if you look at labeling the data, is quite expensive. You need to put people over there to label the data, right? You need to put people who can look at the picture, or who can look at the text document, or who can listen to the audio, or who can look at the tables, what is there in the table, and label it, right? That's the, so, but most of the work in machine learning and deep learning has happened in supervised learning space. But it will be great if we can avoid not labeling the data. Right? We can avoid all that expenses, and we can save on time as well, right? I mean, it costs time and money, right? What other thing we can gain by unsupervised learning over supervised? Suppose somebody said, okay, I'm giving you label data for free, right? And so the cost is not a problem. What other things unsupervised learning can solve, which a supervised learning cannot solve?
find out hidden patterns which a human mind can't.
Which cannot. All right, so I think I'll just wait and make sure you have something there rather than me. So yes, I mean, essentially what happens is in supervised learning, we are constrained by what we know. Right? What humans know, we are constrained by it because we actually label things based on what we know, right? And in unsupervised learning, we do not constrain machine with that, right? We do not constrain machine because machine is free to learn whatever it wants to learn from the data without worrying about our constraints. So the network was called LipNet. Essentially, it was for people, and I mean, there's a practical use case because suppose you're on shop floor, in a factory shop floor, which most of us don't go to, and we all work mainly in IT industry and nice rooms, AC and all, but there is manufacturing industries out there where the workers work on the shop floor with a lot of noise, and they cannot hear each other, right? They have to shout. Now, what if I can build a model which can basically look at the person who is speaking, whom I cannot hear, and basically generate voice which comes to I can hear in my microphone or something, right? So that's possible. If there's a practical use for it, people may not be able to speak as well, but they can move their lips. So you can actually learn what the person is speaking by looking at their lips, how the lips moving. Right, that's what we do. We move the lips to change the air pressure around our mouth, and then it turns out to be sound, right? So yes, it is possible and has a beautiful use case. But getting back to our unsupervised learning, basically the supervised learning lacks new learnings. It's basically bounded by what we humans have learned, right? It's bounded by what we humans have learned, but unsupervised will allow machine to kind of run free. Right? So let's take an example. Chess. This is, everybody understands chess. So now, I mean, for a very long time, we found it very difficult to build a computer program which can defeat humans. Humans means like, people who play chess at the highest level. We found it very, very difficult. Now, in chess, we know everything. I mean, we know how pieces can move given a scenario, right? So it's not a kind of a difficult. It should not be a difficult problem. What makes this difficult is this, right? This is what makes it difficult, right? How many moves? 10 raised to power 1, 2, 3, and this is a very, very, very big number, right? I mean, sometimes we are not able to appreciate, more than a billion, or somebody says Ambani has billions of dollars, and I have no clue. I mean, don't care, because for that number doesn't mean anything to me, right? So similarly, this number is so big, it's hard to understand. So we can just try to compare with something which we kind of relate to, like atoms. So every time I hear about atoms, we keep saying that they're very, very small, and we have billions of them in this small space, right? Atoms is so small, nobody has ever seen it, right? So the number of possible moves in chess is actually more than possible atoms in our observable universe. So that's how big the number is. But having said that, in 1997, IBM did have a machine called Deep Blue, which defeated Garry Kasparov, who was the world champion at that point, and which was stunning result. People were stunned. I mean, Garry Kasparov to this day cribs about that, that outcome. But what we did is, of course, we used a lot of logic, but we used a lot of computing power. We did a lot of parallel computing to calculate all these moves and see which one is the better move and go with it, right? And we defeated, world champion at that time. We means the machine defeated it, not the humans. But let's look at another problem. What is this one? This is called a game. This is Go. Again, I have no expertise in this area. I am talking because we're learning machine learning here. So apparently this game is played in East Asian nations like China, Korea, Japan maybe. And this game is being played for last 3,000 years. So there is a lot of literature available on this game, right? So there are schools on Go apparently, where kids are sent from the age of 5 and all, where they learn Go and then play at professional level. And so why are we talking about Go? Is that's the number that we have to deal with, 10 raised to power 360. And Go has only 2 type of pieces, black and white. I mean, in chess we have quite a few, like 8, 9, maybe 10 different type of pieces, but in Go only 2 type of pieces are there, but number of possible moves are 10 raised to power 360, which means we cannot actually apply brute computing power to kind of have all those calculations done. It will take probably hundreds or maybe thousands of years if we try to do that before the next move gets made, because that's how much power, how much calculation this is, right? Apparently in Go, at every single step, the number of possible moves is equal to the total moves in the chess at every step. That's how big this number is, right? But having said that, in March of 2016, we had DeepMind's AlphaGo machine go against Lee Sedol, who was the world champion at that point, and it did defeat Lee Sedol, and then it was like the score was 4-1. It was not even close. It was not even close, and but the key thing was it was not through brute computing power, right? It was not too many computers running in parallel. Rather, it was where machine learned to play Go, just like the humans do. It learned to play Go just like we do. We keep practicing and keep getting better at it, right? So that was an amazing result for AI, where people said, and apparently there's a movie now on this AlphaGo on Netflix. If you are interested, you can watch how they came about and build this machine. And for next 1 year, AlphaGo played thousands of players, and it never lost again. It never lost again, and it retired in 2017 June or something, because it has defeated everyone out there. It never lost again. It had another match with a world champion called KG in China, and that score line was 3-0. So that's how good it was. It never lost again. It never lost again to a human. It never lost to a human. But it lost to a machine called AlphaZero. It lost to a machine called AlphaZero, and the score line was 100-0. Right? Both were AI machines. What is the difference? I mean, why a machine can defeat another machine so badly, and not just any machine, a machine which has defeated every single human out there who plays Go or who's willing to go against that machine, right? So what was the difference? The difference was in the way the machines were trained. AlphaGo actually learned the game of Go with previous games that humans have played. It was given the data that how the people have made moves at different scenarios. It learned from there. And AlphaZero training was totally different. It was not given any human played game to look at. It was just asked to look at the board and come up with a move. So it took quite some time, and it was playing against itself. It was just playing against itself. Only thing the team was doing is making sure, whenever it makes a incorrect move, they point it out that, hey, this is an illegal move, right? As long as it's a legal move, they allowed it to learn, and they trained it for a few days or maybe weeks, and it got so good, by playing with itself, as that it actually defeated AlphaGo that badly. 100-0. So what happened? Because we did not constrain AlphaZero with human knowledge, it found ways to play this game in which we humans have not thought of. And that's the power of unsupervised learning, where we are like avoiding the constraints of there were constraints, slight constraints, but again, for the most part, machine was learning on its own. And that's the power of unsupervised learning. So we all actually want to build great unsupervised learning algorithms, but it's very hard to do, right? It's very hard to do, but we're making progress. And this is the kind of Mecca of AI. That's where everybody wants to go and not have these labels, so that we can actually learn more about this world than we already do. Right now, supervised learning will tell us whatever we know only, right? Nothing more. But unsupervised can do that. All right. So I just want to make sure that we understand why, we basically sometimes overlook unsupervised learning, but this is a very, very powerful field where a lot of money is getting spent, right?
But here, why we consider this as unsupervised? Because we already have a target, that win or loss.
Correct. That's correct. It's in a way, yes. But it's partially very, very true. It's not that it needs to figure out what this game is. We have given it that. That's what I said. It's not completely unsupervised, but the way to play this game is completely unsupervised. Only thing is the outcome we will tell it, and what are the illegal moves we are going to tell it. It's not completely unsupervised, but for the most part, it is. We are not telling it how to play it, except for the outcomes. More like yes. Right? So but thing is, it's basically not learning from humans, right? From the labeled data. Right? It's not learning from the labeled data. Right? So now, having said that, so now let's look at something called PCA, right? This class is about principal component analysis, and one of the unsupervised learning algorithm. So let's see what problem we are trying to solve. First of all, before learning anything, we should try to see why we need to learn it. Otherwise, skip it, right? It's not school or college where you need to pass the exam, right? You should be able to learn only things which can help you solve a problem, right? So let's first look at a problem. So we have this data, where you have company and then company name and the market capitalization. I can easily plot that data on a single line because there's only one axis, and I can essentially draw this. Okay, this is how the data looks, right? ABC, based on the value of their market cap, because there's only one dimension, and I can also cluster them looking at them. Hey, this is maybe that one is large cap, another is small cap companies, right? It's pretty easy. Now, if we have two of them, we can still make it work. We can still plot it easily, right? If we have we can do a revenue as well as market cap and still categorize, cluster them, right? What if you have three? Can do it 3 dimension, right? I mean, we can, although it's a poor attempt, but I hope it's but we can do it, right? Trust me. It's not I'm not a great visualization guy, but we can do it. We know that. We have the capability. What about 4? We can do with colors, or maybe sometimes we can use the sizes. What about 5? I mean, they're getting difficult, right? I mean, and again, we are looking at the structured data. For example, if you have an image or image, maybe we were able to visualize, but if you have high dimensional data, like you have thousands of columns in a table, and you need to visualize it, it's basically you're out of options there, right? It's not a big deal to have few hundred columns in a table in corporates, right? And not just with structured data, even with unstructured data, we can we will find it hard to work with more than 4 or 5 dimension once we run out of colors and the sizes and all, right? So that's one problem we need to solve is how do I handle higher dimensional data? I want to visualize that data, right? I want to visualize that data, but how do I visualize it? But that's the one problem I want to solve in this class, right? If suppose I have 500 columns, how can I bring it down to say 2 or 3 or 4 so that I can visualize it, right? That's the first part. Right. So what is the second part? Let's look at what is this. So how many dimensions do we have here? Right. The 2 dimension, height, and what is that? The other one? Okay, this is a trick question, right? Sorry. Okay. So apparently, altro is height in Spanish. It's height in Spanish, and maybe they have different measurement, maybe centimeters to this thing and all. So how many dimensions are really there? 1, right? So I mean, unless somebody knows Spanish, we may continue with 2. And a lot of times, this is what happens. It's not extreme example. What happens? We end up, a lot of different people keep updating a table structure over a period. So you keep dumping more and more columns. And because we IT people have no clue what those columns are, because those columns are given to us by the domain experts, like finance, manufacturing, and all. So we keep adding, because for us it's just another column. We can add column, right? So we keep adding and it quite often you will have columns which are maybe a duplicate or kind of can be derived from each other, right? So you see that problem. A higher dimension may not truly be higher dimension, right? So let's look at another example. So you have skidding accidents, water pipe burst, school closure, snow expenses for different geographic areas, and patients with heat stroke, right? Yeah. So how many dimensions are we looking at here? Now everybody is serious. This should have been the first example. How many dimensions are we looking at here? 5, 6, or 2? 2? It's 2. Why we say 2? Sorry? Like what?
What is actually patient's with some based on the geography area?
Huh.
Type of accident.
Okay. No, that way it is actually 6. That way, I thought answer is 2, but why? Why? How many? I mean, if you look at the table, it is 6 dimensions. I mean, 6 variables in the table or columns in the table, and but what it has to do with patience with heat stroke? It's a good analogy. I mean, it's a good thought. It's a good thought. But we have patience with heat stroke. It's true. I mean, I told you that. You need to give me why it is true. It's a planned thing. I mean, okay. I mean, that we are not counting here. We are unplanned. It should be unplanned school closure. All of them are related to the temperature of that geographic area at that point. Whenever we collected the, if it's very cold, you might have, water pipe burst or school closure because there was snow there, and you might have skidding accidents and all that. Or if it gets very hot, people might die with the heat stroke. All of that, it can be replaced with just one dimension, which is temperature, right? If we know that, I mean, this is all related to temperature, right? So what we are seeing is actually the true dimensionality of the data may be very, very less, very smaller than the observed dimension. Observed means like we look at, there are 6 columns, but actually there might be very few dimensions out there, right? Very few dimensions out there. So we want to see what is the true dimensionality of the data, right? We want to work with, because true dimensionality, you are working with lesser data. That means you have a better chance of getting things right rather than having all that noise thrown in at your way, right? So another problem. So first thing is we want to visualize the data, higher dimensional data. We want to look at our true dimensionality so that we can understand what really is there in the data rather than looking at thousands of columns. Another is a problem that we want to solve called curse of dimensionality. How many of you are aware of it? Heard of it? Okay, yes. Yes, that's okay. All right, so curse of dimensionality is like, let's look at the example. So in vision, for example, we have 1,000 by 1,000 pixels image. So how many data points do we have for each image? 10 to the power 6 is called a million, right? So a million features, is million correct for a 1,000 by 1,000 picture? It could be. We usually have 3 dimension, red, green, and blue. So 1,000 by 1,000 means 1,000 by 1,000 by 3. So it's actually, we are looking at 3 million features in an image. Similarly, if you look at text documents, we are actually looking at billions of phrases in just one language. Right? And we have to account for all of these, right? We have to account for all of these to better understand the vision, images or the text documents, or in structured data, it's a little easier for us because you deal with maybe 100 or 200 or 500 columns. But in case of unstructured data, it gets extremely difficult. The number of features just explode. All right. So now this is an image. So how many dimensions does it have? How many possible values could be there in this space? How many different combination of values could be there in this space? Okay, so if I just replace each cell with 0 and 1 alone, 0 and 1, apparently there will be 2 raised to power 784 possible pictures like this. Possible pictures like this, 2 raised to power 784. What is 2? 2 is number of possible values for individual cells, 0 or 1, right? And what is 784? How did I got 784? Everything is from this picture, nothing else. All right. So what is the picture? So 784 pixels, and because this is black and white, I have just one dimension in the depth, right? So that many possible values are there, right? That many possible values can be fitted in this small space, but most of them numbers? I mean, if you look at, will most of them be numbers? I mean, if you have, if you put zeros and ones here or here and here, what will happen? What if you do if you run through this example in a notebook, you can try it out, and you will get that notebook with you. You can try out. You will find that most of the pictures that we generate are not really numbers, right? Most of the pictures that we generate are not really numbers, rather, some random things, right? The actual number of values which generate numbers are very few. But what we do, we make our model learn all these things, because the model has to go through, learn all 28 by 28 space. Again, as the dimensionality increases, you get lot of noise out there, right? Now let's look at like a simple example. Here, suppose we have 10 samples. We have given 10 examples, and there's one dimension. Imagine that market cap for individual companies, right? And we can plot it. Basically, suppose there is a large cap, mid cap, and small cap, right? There are 3 different reasons in which we can classify those things, right? Now, so I said 3 reasons. Suppose if I had 2 dimension but same number of example, I had only 10 examples, but now I have 2 dimension, market cap and revenue. What will happen? It'll become like this. It'll become like this, where we have to plot different companies in these 9 different regions, because you have 3 regions per dimension, 3 regions: large, market cap large, small, and medium. What is the difference between this? What do we feel any difference?
Single dimension.
Single dimension, yes.
World formation.
So we are getting more. So what we are saying is, basically, because we need to basically look at now 9 different reasons. In a way, we have to divide our data into 9 different possible regions. What is happening is, in each region, the number of possible examples have reduced drastically. Some region has just 1, some of them don't even have any data, right? Some of them don't even have the data, right? And if we go to 3 dimension, it will be 27 regions, and you will be left with only 10 examples. So that means a lot of places you will not have data for machine to learn, right? So that's the curse of dimensionality. As your dimensions increase, essentially what happens, you get fewer and fewer data points for your machine to learn. For your machine to learn, you get fewer data points. And as we know, with machine learning, we need more data, not less, right? So what we want to do is basically, we want to deal with higher dimensional data and basically make sure, why we want to deal with higher dimension data. One thing is, we want to, first of all, be able to visualize it. Second, we want to work with true dimensionality of the data, not really the observed dimensionality. Third is, we want to make sure machine has enough data in each dimension that we give it, right? So that it can learn better, right? Those are the three problems that we want to solve, right? And that's why we want to learn PCA, not for any other reason, not because it's part of the curriculum. That's one thing, but you're not going to have a test on this, right? Exam. So you basically want to solve a problem. So one thing we can do, of course, is some simple thing is, we can use domain expertise to build feature engineering, like somebody, like for example, that temperature example, we were the domain experts, right? We know about those things. So we could say that, hey, why not replace it with temperature? That could be one thing. But a lot of times, suppose if you are working with data which is not in our domain, Like for example, I don't know finance, so I can take help from a finance guy, say, hey, can you tell me if there are any redundant columns here so that I can throw those away? Or can I combine the columns to reduce my dimensions? Right? That's one way. And another is we can reduce the dimensionality of the data in using some algorithm, and we can basically what we can do to dimension is we can either keep fewer features, like we had 100 columns, maybe we just work with 10. 190 we just throw it away, right? Or we can create some new dimensions which better represent the data, but hopefully the number of new dimensions are much lesser than what we started with, right? So the first approach, so the key thing about dimensionality reduction when we look at is because we are trying to throw away the data. So, right? I mean, when we say we are reducing dimensionality, we are throwing away the data. So there has to be some method to throwing away the data, right? You cannot be just random about it. So what are the goals? That first of all, the goal is that we want to represent each example in our data with fewer dimensions or fewer variables, right? That's the first thing. Second thing is we should be able to preserve most of the information that is there in the data, right? We do not want to throw away the information in the data. We want to throw away the data for which information might already be available somewhere else, or we can capture that in some other dimension and use it, right? So the idea is not to throw away the information, rather throw away the data which is not helpful. You see the difference, right? So that's the goal. Now, so there's something called feature selection. Has everybody gone through feature selection class? Right there, what we do is we just pick up feature selection. The answer is there, of course. Forward selection, backward selection, and right. What we do is we basically try to, suppose if we start with 10 or 15 features, we might want to be just throw away 10 of them, depending on the criteria, and focus on 5. Right? So we throw away 10 as is, right? And then keep 5, right? That's feature selection, but there's another thing called feature extraction. Feature extraction is where we actually don't throw away the data as is. Rather, what we do, we create new features or new dimensions based on the existing data, right? And then we are free to throw away the data which we started with, right? So that's feature extraction, and that's where the algorithm Pca fits into. It basically tries to build new features which actually capture most of the information that is out there in the underlying data, right? So, all right. So let's understand how it works. All right. So first, what we will try to do, we'll try to visualize how things work before going into math, because math can make things little, intimidating. All right. So we are starting with this. So how can Pca help? Okay. So let's see what all Pca can do before we know how to do Pca, right? So first of all, it can create new features. Right? Then, of course, can make 2D graph from 4D or 10D. And we will look at where we are going to convert about 700-800 or maybe 100 dimension data to 2D data and see if it helps. Right? So we'll take a look at that. So it can reduce and can help you visualize a higher dimensional data. Right? That's the first thing. Right? It can also tell us which feature is actually most important in separating the examples. It can tell us which feature is most important in separating the examples. So it can do that as well, right? It can do, and we will see how it does that, right? We'll look at an example. It can also tell how accurate the graph is or how accurate your new data is. What does accuracy means here? What do you think accuracy means? What are we trying to do with dimensionality reduction? We're trying to reduce number of feature, number of dimensions. But what is our goal when we try to reduce dimensions? We do not lose information. So it can basically, what accuracy here means is how much information is being kept in the new space, in the new features. It can tell you that. Is it 100%, 90%, 85%? And it can give you a mathematical number to assure you that you are on the right path. Right? There's no point saying that a lot of information will be kept. What is that lot? We should have a number for it. Right? So PCA actually can give us that number as well. Right? Then what else? So let's see how PCA works. So what we will do, we'll start with a two-dimensional data. It doesn't make sense though. Right? You need to start with three-dimensional. But to make our life easy and to draw these graphs, I'll start with two-dimension. But the concept remains same. So two-dimension, like feature 1 and feature 2. And we have, so what we do is first, we just plot the graph. Against, x-axis is feature 1, y-axis is feature 2. We just plot it with the numbers that are given here. Right? Simple thing. Right? Yes, any question? Okay. So first we just plot it. And then what we do is we calculate the average or mean of the individual features. So we have two features, F1 and F2. So we are going to calculate the average of the features. So we got 5.83 and 3.83 for F1 and F2. And what do? We plot that as well. That X is nothing but 5.83 and 3.83 value. Right? And then we shift the origin. What is the origin? Origin of this value. 0, 0. We shift it to X. We shift it to X. Right? The X becomes our origin now, and you have points moving. But their relative position is still the same. Although actual values might change, but their relative position is still the same. This one is still the the left bottom part, and that is still the top right part. Right? So the relatively the points stay in their position, but their actual numbers representing those numbers will change. Right? So what we do is first draw all the points, then we basically calculate the average and draw plot the average, and then shift the origin to the average points. That X in this picture. Right? Simple so far? Right? Yeah, yes. I mean, it has to be because this is two-dimensional data, right? So it's 5.83 F1 and 3.83 F2. So that's how the values will come. Right? It will be two-dimensional. Yes, it is two-dimensional. Right? It has to take both values. Right? Then what? Then what we do is we just draw a random line. A random line like this. Right? By the way, this is just for visualization perspective. We do it all through math, which we will learn. Right? So, but visually it's easier to kind of understand what is going on. So we just draw a line which a random line, which any kid will do, or maybe not. So what do we do with this line? Then what we do is we keep rotating this line. We keep rotating this line so that we find the best fit line. Now the question is, what do we mean by best fit line? Right? What is mathematically we have to have something to rely on. Because there are infinite positions when you rotate it. There will be infinite positions, right? So what does this rotation means, and what does this best fit line means? Sorry? What explains maximum variance? What is that line?
Minimum.
The variation.
Sorry?
Some of the squares from the point to the line should be.
Okay, yes, that's right. So basically what do we do is basically to find out what is that best line is, what we do, we basically project. We project the points on the line. We project points on the line like this, like, in a perpendicular fashion. Right? We project the points on the line, and so we can project this on any line. Now, what is the best line? So, best line will be until the projections or the distances are smallest. So, until the projections are smallest, right? Now, there's another way to look at it. There's another way to look at it. As one way is to say, okay, the projections are the smallest, or the other way is the distance from the origin is maximum. Distance from the origin is maximum. What is the new origin? The x1. Distance from here, this is maximum. This is smallest, and this is the maximum. It actually means the same thing if you look at that Pythagoras theorem, right? Because one thing is fixed, so you can work with only two dimensions, and if you reduce one, the other has to increase, right? So because why I say that? If this is the line, suppose this is our line and point is here, when we project it here, when we project, suppose this is going to be 90 degree, this is 90 degree, so suppose this is A, B and C, right? C is fixed, right? Point from the origin is fixed, it cannot change, only this line can rotate, right? C is equal to A square plus B square, square root of this, right? So if A reduces, if we reduce A, B has to increase to make sure the C remains same, right? So that's why either we say that projections are the smallest or the distance from the origin is maximum. So usually we go with the distance. It's easier in math to calculate that, right? So we go with the distance, right? So we try to maximize these distance from the origins to the projections, to the projections on the line, right? And there is a name for this. Alright, so how do we know the best line? Is, of course, we said we can calculate the distance, and because the distances could be both positive, like from here to here, or what we do is we basically square them up, right? We can square them up and say, okay, that's SSD, sum of squared distances. You are very familiar with this one, right? It's like mean squared errors, right? Sum of squared errors. So wherever the SSD is smallest or highest, because we are trying to maximize these D's, right? So that means wherever the SSD is highest, we will get our best fit line, right? We will get our best fit line. Now, what do we do with that? So what is best fit line? Suppose this is the one I drew just now is the best fit. Let's assume, right? I mean, so this is the best fit line is called PC1. The best fit line is called PC1, principal component 1. So what we do is, before we go into what PC1 means, we will basically we will calculate what is the value, or what is the ratio of F1 and F2 for this line. How do we calculate ratio? How can we calculate ratio for F1, F2 in this line? We can select any point on this line, right? We can select any point on this line and see what is the F1 and F2 values for that point. And then, because the ratio will remain same, it's the same line, the ratio will remain same, and F1 is like F1 is 2 times F2. F1 is 2 times F2. So for what it's saying that F1 actually is 2 times more important than F2. F1 is 2 times more important than F2. Remember when we talked about PCA, one of the things it can tell you what are the features that are more important. So in this example, F1 is twice the important has twice the importance of F2. Now, why? I mean, what? So if we can write it, and then usually we write this ratio as a unit vector. So what is a unit vector? So you keep the one, top as 1, and then you calculate the ratio of others, which will be less than 1. Right? That's one way. And this unit vector is also called Eigen Vector of PC1. So there are a lot of terms here. Eigen Vector of PC1. We'll talk about it. But we have not clarified what is PC1. Let's hold on Eigen Vector. Right? We've not said what is the PC1. And then before we introduce another term, Eigen Vector and Eigen Value. Yes, please.
So you want to say that before PCA, we always need to standardize it.
Before PC, yes. I mean, we usually do. Because it's all. I mean, you are going to calculate the projection, and a bigger number can make can force it to us. Yes, we usually normalize the data before starting the PC. But here we have not done it. Just for illustration purpose. But usually when we use math, we have to normalize our data. Almost for all the machine learning algorithms, right? Right. So we are introducing two new terms, although we have not talked about PC1 itself, but we are introducing two terms called Eigen Vector and Eigen Value. But now to think of it, Eigen Vector is the ratio of the features for PC1, Eigen Vector, and Eigen Value is the sum of squared distances. Eigen Value and Eigen Vector. Right, those are the two things we are going to learn about a little more. So just to recap quickly, first of all, we calculate the mean of each feature. We draw it. We calculate the mean. Then we move the origin to the mean. Right. So we shift the points. Then we draw a random line and project points, and we find the sum of squared distances. Right. Which we want to maximize, and then we rotate the line to find the best fit or the maximum value of SSD possible, and that line is called PC1. That line is called PC1. Of course, we know that we've also find the feature ratio to see which feature is the most important one. Right? Based on the PC1 line, we can find the ratio of features, right? So we can look at that, and we know which feature. Again, here we are just talking about 2 dimensions, so we can deal with a one line. But if suppose this is a 3-dimensional data or 4-dimensional data, will PC1 will be a line? It will be a plane or a hyperplane. What is hyperplane and plane?
Plane is for 3D.
And hyperplane is just it's just a common term we use for plane of different size, right? So now, and we calculate the unit vector, which is called the Eigen Vector, and we also calculate the SSD, which is the Eigen Value. Quite a few terms, right? PC1, Eigen Value, Eigen Vector, SSD, and the unit vector. Right? We calculate all these. Now, why are we doing these? Right? The question is, why are we calculating all these things? What does it even mean? Right? I mean, so what is? Let's look at before we go further. So let's look at this one. So what does this PC1 means to me? The PC1 is the new feature of our data. PC1 is the new feature of our data. How are we calculating PC1? How are we calculating PC1? Of course, we went through all the steps, but ultimately what PC1 is, it's some combination of F1 and F2. Do you agree? Right? That's what we say, the ratio of F1 and F2. So what we do basically to calculate PC1 of Our old points is we basically multiply by with those weights of F1, F2, and we can get a new dimension, new feature. So we got a new feature, PC1. So that's the new feature. So what we are trying to do in PCA, or in case of feature extraction, is what we do is we basically use our existing features and build up new features on top of it. And hopefully the new features can be a smaller set than what we started with. So we are creating new features and we are going round and round, but there is a reason for doing that.
But we are losing information here.
We are losing the information. Ultimately we do not, but yes, we throw away some information. To keep 100% of the information, it's very hard. But what we will learn that even if we start with 100 dimension, and if we reduce it to 3-4, we still get to keep maybe 90-95% of the information, which might be pretty good. And not just very good, might be actually desirable. To throw away some information. Why it might be desirable to throw away some information?
Time reducing costs,
I mean, that you get by reducing the dimension, but why throw away information?
Reducing noise.
Exactly. We will usually, all our data set have some noise, and we are not trying to capture that noise. So through by reducing the number of dimensions using PCA, we can actually throw away the noise. So it's not a bad thing, right? So not only you get fewer data points, you actually get better data set. Right? So it's don't think every data has perfect data, information in it. There's a lot of noise present, and with this approach, we can actually throw away the noise. Now what we have the PC1. So we got the new feature. Now we need to see how much information is being captured by this new feature, right? We will learn about that because we need to understand mathematically how much information got kept. I say, okay, we are going to capture 90%. How is that 90% coming about, right? So we will just hold on to that. We will come back to that. But is everybody familiar or comfortable with how we are calculating PC1? It's a combination of existing features. Yes, please. Maybe suppose you have two dimensions: market capitalization, and revenue. So what you are doing, you are creating another dimension called PC1. Another data point, so this is, for example, company A, B, C, like that, right? Suppose you had 1,000, 500, 900, something, and then 6, 5, 3, some values. So what you are doing, you're combining these and creating a new value, say 52, 61, 73. Now, what exactly it means, it's hard to say, but ultimately it's a combination of existing data points. 50% of market cap, 30% of revenue, and maybe 20% of number of employees, whatever it is, it tries to build a new dimension for you. That is so. Okay, that's where this role. Okay, now it's hard to say what. Now your model will depend on, say, PC1. Suppose you say, hey, it's influenced by PC. Suppose you have multiple PC. We'll talk about multiple PCs. So question from her is, if I have these new dimensions and if I train my machine on these new dimensions, how do I explain it to my employer or my customer, right? Hey, what is my model doing? What feature it is dependent upon? Because PC1 is like, nobody cares about PC1. But so how do we explain? We explain that if suppose it's highly dependent on PC1, for example. Now I have to explain what PC1 is. PC1 I can explain saying that PC1 is 50% market cap and 50% revenue, or like some look at the ratio. So the ratio can tell you what feature is important for PC1. Right? Here, F1 is twice important than F2. Right? So you can get down, using PC, you can get down to the features that you started with. It's not that you are losing that information. So it's not completely, it's a linear combination anyway. It's a linear combination anyway. Right? So this is what, that's how you can explain it. Yes, please.
How the Eigen Value getting presented? How does it simplify?
How does it, okay, so Eigen Value is signifying the ratio of the features.
Not the vectors. Value.
Okay, sorry, Eigen Value. Okay, we'll talk about Eigen Value in a minute. Again, to basically bring it forward, there has to be a reason, otherwise, it's just waste of time. So we'll look at that in a minute. But yes, we will talk about that. Yes, good question. I mean, how do I know I should use only 2 out of this 10? Right? I mean, I want to keep, if I'm saying I'm going to reduce number of features, so how many should I have? Right? And if and what is the trade-off? What is the trade-off? Right? Ultimately, we are throwing away some data, some information, although probably not the data, because we are capturing what we are doing. We are creating new features using all our data, existing data. So it's not completely throwing away as is, but what are we capturing? Right? We will talk about that. But everybody understand what is PC1? It's a new feature, which is a combination of existing features, and that combination is given by the ratio between between the features, right? So that's called eigenvector of PC1. All right. So let's now we have PC1. Right, this is suppose our PC1. What we will do? We'll draw a line perpendicular to it. This time we are not going to rotate it. Enough rotations. Enough rotations done. Now we can just quickly move and draw a line perpendicular to our PC1. Right? PC1. Now that becomes PC2. This is our new feature. And so if you have, suppose, we started only with two features in our original data, where we only started with 2. So we will have only 2 PCs, PC1 and PC2. Suppose you had 100 features to start with, then you can go up to 100 PCs. Again we come back to 100, right? What is the point? Right? You started with 100 features and you did all these calculation rotations and you come back with 100 features again. What is the use? Right? So we have to look at the role of what eigenvalue brings to the table. Eigen vector, we understand, gives us the new features, but what does eigenvalue means? What is eigenvalue mathematically? SSD. So, right? It is sum of squared distances, right? So what eigenvalue does is basically, suppose we have two features. So PC1 and PC2 we got, because we started with only 2 features, so we could get only 2 PCs. And suppose we got 18 and 3 as SSDs, right? 18 and 3 as SSD. And if I write it in percentage term, it will be like 85. First PC1 is 85.5, the SSD for A, and PC2 will be 14.5%. Now, what did this percentage mean? Importance, yes. It basically means how much variance in the original data is captured by that respective PC. And because we do all the rotation in the beginning, PC1 usually is the PC which captures the most variance. PC1 will always capture the most variance in the data. Variance is the information in the Variance is a representation of information in the data. How varied is my data? Right? So that information is captured by the eigenvalue or the SSD. Right? So now, now of course the 14.5% in this case is the variance captured by PC2. Right? So if you have 100 features to start with, you come up with 100 PCs. That means 100 SSDs or 100 eigenvalues. All of them will add up to 100% variance or the information in the data. Now we have to take a call. Right? We have to take a call. So what we do? Okay, so this is the new feature. I mean PC1 and PC2 we talked about. Let's hold on to this. They will be. Don't worry. You should get it on Olympus. Okay. So so suppose you have 5 of them. I think the slide might be a little ahead of, but I'll just describe it. Suppose you have PC1, PC2, and PC3, PC4. Right? Suppose we have 4 features to start with, and we ended up with 4 PCs. And the values of SSD is say 20, 6, 3, 1. Usually, as you increase, you go from PC1 towards the higher dimension, the SSDs will reduce. SSDs will reduce because that's the maximum we are trying to capture in PC1 itself, right? So what we do is basically if you add them up, it is total is 30. That means this is about 67% of variance, and this is about 20%, right? And this is about 10%, and this is about 3%, right? So that's how the different different PC captures different variance. So you might decide, hey, I want to keep about 85% or 90%. If you want to keep 85% of your information, then you can keep just PC1 and PC2 and let go of PC3 and PC4. So that way you get down to 2 dimensions. If you want to capture 90% or more, then you keep PC1, PC2 and PC3. And the PC4 can be thrown away. Right? Because it captures only 3% of the information. You still keep 97% in this case. This is just a made up example. When we look at a real example, it actually, PC1 usually does even better. It goes very, very high. Right? With all that rotation, it goes very, very high. Right? So now, so this is, we can calculate the new values of our data points in terms of PC1 and PC2, and becomes our new graph. This becomes our new graph, essentially this is how the data will look like after we have turned it into our principal components. Right? So the idea is to capture the maximum information in the data in PC1 and then draw a perpendicular line to it to capture it in PC2, then another perpendicular line to both PC1 and PC2 to get PC3, and then so on. So what is this perpendicular thing is? What does perpendicular means in this case? Perpendicular means is basically these features, the PC1, PC2 are independent, basically not correlated. They're very independent, right? And you have learned about like how correlation can sometimes create problem. So we are basically avoiding that here as well. You're basically creating completely independent features because you're going straight away 90 degree, right? So that's the idea behind principal component analysis, where we build. So what do? We basically build new features, combining existing features. We also understand how much variance or information is captured by each of these new features, and depending on our judgment, we can throw away some of the PCs to reduce the dimension of our data. We can still, yes, okay, yes. So how we can do perpendicular? Let's,
PC1 is a given baseline.
okay, So let's look at this one, right? So here, suppose we say it's like F1 is 3 and F2 is 1.5. That's what we saw, right? Similarly, if we take a point here, I mean, we basically, when perpendicular, saying that it's this becomes minus, right? This F1 will be minus 3, right? You can, it's just a, you are basically coming up with the new coordinates, which is mirror opposite to it. It's very easy. Yeah. So like if F1 and F2 are 3 and 1.5, right? What will be the perpendicular of it? If you look at this, I mean, if I draw a point here, it will be minus 1.5 and 3. So 3 and 1 minus 1.5 is perpendicular to 3 and 1.5.
So let's say I have drawn one more line which is P, which is at an angle less than 90 degrees to PC1.
Okay, so that will not qualify for to be called as PC3. Every PC, again, we are just talking about lines here because we are just dealing with 2-dimensional data. We might be dealing with 100 dimension. That means each PC will be a plane, and each PC will be 90 degree to the all other PCs, not just to the immediate one, all other PCs.
PC1 will again shift its position from the initial position.
No, PC1 will remain fixed. PC1 will remain fixed. We calculate PC2 because if it's fixed, we know how to draw a right angle on this. Once these two are fixed, we know how to draw another angle at it. Then we draw another angle on all three of them, perpendicular. So every PC will be perpendicular to each other, not to some just one or two. So let me, sorry, go ahead.
So if you do correlation analysis among the PCs,
yes, it will come out to be 0, all of them. That's it. They are independent features. They are built like that. No, so basically what we are doing is so what we will do, we will basically multiply this. This is multiply the original data with 1 and feature 1 with 1, feature 2 with 0.5 to calculate the new value. Similarly for so the PC2 we multiplied by 1 and minus 0.5 to get the next value.
Right, but then the original value is losing its original.
So we are not. So after we calculate PCs, we don't really care about the original data. We are going to use the PCs to feed it to the machine to learn from the data. We are reducing the dimensions, and also at the same time we are trying to capture as much information as possible in the original data.
Relative to some baseline, the PCs are getting back, right?
Right. So yes, so PC, I mean, once we do PC1, we can easily get all PCs. Because it's just a projection then. It is not dependent on data anymore, the underlying data. It's all projection on PC1 and then PC2 and then PC3 and PC4. At that point, we are not really looking at our underlying data, right? Because once you have PC1, only for PC1 we look at the data. After that, it's all perpendicular to the PC1.
So after prediction, we have to find the original models will be there. Suppose our content is 5, and in that 5 with the value is prediction.
Yes.
Then again convert to 100.
You can convert it back to 100 because you know how PC1 was built. It used one ratio of 1 with the first feature, 0.5 with second feature, so you can go back to the. But having said that, because you have thrown out some of the PCs, you may not be able to capture your data completely. Right? If you threw out some PCs, so that what that means is you will not capture that values of to 100%.
That multiplication factor was the Eigen
Vector and Eigen Value. Yes.
and that is unique for each piece.
Each PC will have unique Eigen Vector and Eigen Value. Yeah, not really. Only PC1 gets rotated. Only first line gets rotated to get PC1. Once PC1 is there, then we just draw lines. I mean, we don't really care about the underlying data because we have found that line on which we have to base all our new PCs.
So for PC1, we are considering F1 and F2.
Yes.
If we are considering two features, we are getting a new one.
Correct.
Now for PC2, are we considering F3 and PC1?
No, so we have only two features in this example. So
how are we getting PC2? It's just that we are drawing a perpendicular.
just drawing a perpendicular line. And how do I get the new features? So how do I get the new feature? Let's look at that. Is for PC1 I project, so I get these values, right? For PC1 I get, so these values are nothing but this distances are nothing but the PC1 for me, for the new data. For the existing data, I get PC1. This is my PC1 for first, this data point, this is my PC1 for second data point, this is my PC1 for third data point, right? Now, how do I get PC2? Again, what I will do, I will project my data on PC2. So now this, you can see that it's very near to the origin, but this becomes my PC2 for this. This becomes my PC2 for this or this. I mean, depending on which one we projected. But again, here also we project each point on every PC to get the new value. Yes.
What's the purpose PC2 is serving? Because for PC1 we are already creating a new feature.
Yes. What is PC2 doing there? Let's go back to this line. What happens is PC1 captures the maximum variance, but not 100% of it. We still need, it's not that you can always capture all the information with just one dimension. It's very, very rare, right? So if you have 100 dimensions, maybe you can get it down to maybe 7, 8 or 10, right? And that first 10 will capture say 90%, and then you're good with it. So PC1 will capture maximum, but not 100%. So that's why you have to go to PC2 and then PC3 and PC4, right? So that's how, so every time you have to project to calculate new values of, yes?
Do with Gini index also, right? PCA.
How we do with the Gini index?
So basically Gini index I can actually calculate the importance of the variable. Or maybe information value basis.
See again, so that is more about feature selection. Yeah, information gain and Gini index is more about feature selection, where what you do, you take the original features and say that these first 5 features are my most important one. I'm throwing away 10. But here the major difference between feature selection and feature extraction is you're not throwing away any data actually. All data points are being captured in PC1, all data points are being captured in PC2. There you throw away some of the features itself. Feature selection and feature extraction, remember that in feature selection, we throw away the original data points, some part of it. But in feature extraction, we try to keep as much information as possible from all the data points that are there in the underlying data. So that's a major difference, right? Here we have F1 and F2 both in PC1. So even if we keep PC1, we still have representation from F1 and F2. So that's a major difference. Yes?
If we have more than 2 dimensions, still will PC1 to 3 everything have all the dimensions?
Yes. Yes. So if you have 100 dimensions, suppose you have 100 dimensions, you will have from PC1 to PC100. So you will have 100 new PCs. Then what you do? You will find out what are the SSDs for those 100 PCs and say how much variance each of them is capturing in descending order. And then you say, okay, I want to capture 80%. What are the top 5? I mean, if your top 5 PCs are capturing 80%, then you can throw away the 95 PCs and just keep the first 5. Because they are capturing 95% of the, 80% of the variance or whatever the, usually we try to capture 90% of the information. That's usually the goal. how varied the data is, how they vary, I mean, are they correlated? I mean, take away the correlation. Take away the correlation. How varied the data is? Are they moving, independently? All the data points, with respect to all the data points. Yes, we will keep doing it. So initially we will capture all the PCs. Mathematically, we'll capture all 100. If under dimension, we'll capture all 100, and then we say, okay, I want to capture 90% of the variance. How many pieces do I need to keep? And answer may be, hey, you keep 6. If you keep these 6, PC1 to PC6, you capture 91%, and then say, okay, good, I'm good. Let me throw away the 94 PCs.
So when we interpret PC1, it means that it's some kind of function of this one variable and the second variable.
Correct, exactly.
But when we interpret PC2, how do we talk about it?
Again, PC2 is also a combination of first and second variable. It's a ratio of first and second, but a different ratio. And PC3 also is a ratio of all the variables, F1 and F2 in our case, again a different ratio.
They would be ratio, they would be function of X.
All of them are linear functions of both F1 and F2.
So if you have
In between, they would be independent. PC1 and PC2.
Two are independent, although F1 and F2 might be related to each other.
One can be, let's say, a ratio of 5 to 1, and other can be ratio of 2 to 3. Like
It should be 90 perpendicular. So if unless 2 to 3 is a perpendicular line, I mean, if it's a perpendicular, yes, it can be. I mean, again, that's why we convert it into unit vectors, because then you don't need to worry about 2 to 3 to 5 to 7. You can say 1 to 0.5, 1 to 0.0, whatever, right? That.
But here it's not perpendicular, right?
Here, this one?
1.5 should come up in PC2, right? X.
It's exactly the same thing. I mean, it basically, if you say -3 by 1.5, you can go either way. You can go.
Saying that X should be 1.5 and Y should be 3 there. PC2.
PC2.
PC1 is correct, 3
Okay,
1.5.
okay, let's look at that. Okay, let me rub it off. We can again, yeah, I mean, that could be the case, but ultimately it has to be perpendicular. So if this is the line and PC1, so if this is 3 and this is 1.5, that's what we are saying. So we have a perpendicular line. Perpendicular line. What perpendicular means? I think perpendicular will mean, is it more like a square or something, or right? So you can calculate it. This should be 1.5 on y-axis. On x-axis, it will be -3, right? Otherwise, it will not meet, right? So that's how. I mean, again, we don't need to do it. We will see how it gets done mathematically.
So if two fields are there, it's like highly correlated. So in mathematics, it's like, for example, it's a calculated field. We don't know whether it is like highly correlated or not.
Yes.
So if two columns are there, mathematical space is in a different position.
Yes.
So how do PC?
That's what. If it is highly correlated, it'll get captured in PC1 itself. It'll get captured in PC1 itself. That's why all the correlation part. That's why we are doing all the rotation. Yes, that's what. Yes, what we are doing by all the rotation. Minimum. If you look at the projections, this distance should be minimum, but this will be maximum. SSD we said is from the origin, right? So it's the same thing. It's the same thing. We just have two different names for the same thing.
So ideally, we don't need to worry about the IF in PCA.
Correct. I mean, it's yes. I mean, that's what it does. It basically takes away all your correlation part and makes it features independent. And who doesn't like that? But the data should be linearly separate. I mean, it's still a linear function. F1 multiplied by some value plus F2 multiplied by some value. It's a linear function. It's not a non-linear function. So if your data is non-linear, it may struggle. Remember that. right? Otherwise, it could have been the nirvana we are looking for, right? So it works on linear data. Okay, all right. So is it clear what is PCs? Okay, yes, go ahead, please.
How does it compare to supervised learning where we didn't have all these concepts?
So supervised learning goal is to predict something, what we are telling it to predict. You know, we give the label, predict there's an elephant in it, predict there's a boy in it, predict there's a background in it, whatever we want, right? We here what we are saying that, hey, can you give me, can you reduce my data size? And I'm not telling you how, I want to use these features. I don't know. Can you give me a reduced data which will still work well for my training? In unsupervised, we are not labeling our data, right? We are just throwing data at PCA and coming up with the reduced data set. That's why this comes under unsupervised learning approach. It gives me, if I have reduced data, what is the advantage of reduced data? First of all, a benefit we talked about, noise is thrown out, first of all, right? Which may not think of initially. First of that. Second thing is, I can visualize my data to see how the data looks. Is there any relation between, Second, third is, I can, if machine needs to work with smaller data, it can run faster. And usually with less number of dimensions, what we have seen, machine's accuracy improves. So all those benefits you can derive from it. Yes, yes, rather than we saying, rather than your domain expert coming and saying that, okay, you just remove these data points or combine these data points, we let machine figure it out. There is. We will not go into detail, but I'll show you one example how to use that. Okay, we'll take a look at that as well in an example.
Can we not transform non-linear data and then it will continue?
In a way, yes. So how do you transform non-linear data into a linear data? Exactly. If we can, basically the transform or moving from non-linear to linear requires us to moving into higher dimensional space, which we are trying to avoid. We're trying to reduce dimension, but it will ultimately try us to go to higher dimension and then come back where we started. Right? That may not be very helpful. Right? So yes. So that's we can do that. We can try it out. Maybe sometime it helps, but it will force us to go to higher dimension, which we are trying to avoid because we already are in higher dimension space. We're trying to avoid going to more higher dimensions. Right? Everybody is okay with what PC does. Good thing is you don't need to rotate the line, manually. That was just for understanding what is, what happens. There is beautiful math to do it. Right? So what we will do, we're going to check out the math as well. And so these are the two things we want to calculate, right? We want to calculate the Eigen Vectors, which are the unit vectors which represent the PCs, which is a plane or a line in two-dimensional space, and we want to calculate Eigen Values, right? So very cool sounding names, So we'll see how to calculate these, right? How to calculate these using math, because once we have these, that's it. We are done, right? We have our PCs, we have our SSDs or the variance capture, and that's it. We can easily so how many eigen values and how many eigen vectors should we have, or will we have? It'll be same as number of features to begin with, so it'll be n. Like if you have 2 features, 2 PCs, 100 features, 100 PCs.
Can we create more things? But it's useless, but you can create.
I don't think. That's possible. Yeah. I think mathematically or even when you're drawing the perpendicular in a plane, it may not be possible because you have captured 100% of.
Useless.
It's useless is different thing. I'm just thinking mathematically. Yeah, mathematically whether it's possible or not, but probably not. We'll see the math also. Maybe you can try to see if more than number of features is possible or not. All right. So
I'm just thinking if the number of features are very less, then if we can create
more features, then you use your polynomial and all. Why go to PCA? PCA is to reduce the dimension. If you want to have more, you can add, those logarithmic, polynomial, and whatnot, or you go to just feed it to a neural network and it can build its own features, right? So building more is not a problem. It's doing, using less is problematic for us, right? So now, we will have exactly the same as number of features in the original data, right? Now, this was the slide I was talking about, which we solved on the, basically you will have the Eigen Value, and then you can calculate the percentage variance captured by it. And for example, here if I want to capture 90%, I can just keep PC1 and PC2 and throw away PC3 and PC4, right? So that's what we can do. Now the little harder part, right? So, but let's see. I hope it's not too difficult. So we will go into the math, but before that, I thought we'll spend another couple of minutes to make sure we understand why our data points, the new features are independent, right? So how are we getting our features is by projecting data points on PCs, PC1 and PC2. So if you look at this picture, the red X's are the PC1 points. Now the PC1 is, like for each data point, this is the new value, right? The first feature. And the second feature are these blue values. So if I just rotate PC1 to make it as X-axis and forget about F1, F2, because we are not going to work with F1, F2 anymore. We are going to work with PC1 and PC2 alone. This is how the picture will look like, right? The old data points are gone. We are just left with PC1 and PC2 values of our examples, right? So which means if you see here, each feature is on its own axis, completely independent of other feature. That's what independence means, right? It's visually we can see that because it's on its own feature, on its own axis now, right? Completely independent of each other, right? So make sure we are comfortable with that thought, why we are saying that PCs are independent features, right? All right, so let's
PCs are dependent, right? And features are independent.
PCs are in a way related, yes. Each PC is perpendicular to other PCs. I mean, yes, we are deriving other PCs from earlier PCs, yes. Sorry? 90 degree means no correlation. Independent, that's what we in mathematically we say. All right. Why is PCA unsupervised learning is in a way because we are not giving any labels to it. Yeah, right. I mean, we are just throwing the data and telling it, can you give us data which can capture a lower dimension and still capture the information in our original data. So we are not giving it any label. We are not defining any column for it, that this is what a column means, and still it is able to do that. Still it is able to capture a lot of information and in small dimension space. Unsupervised usually means basically we do not give it any labels, that this is what it means, to how to read. Of course, the algorithm we have to teach. Even the clustering algorithm is brought up by humans, not by machine. Machine still has to follow the algorithm that we prescribe, right? So that part is supervised, but as far as data is concerned, the data is not supervised. We just throw data at it and we get a lesser amount of data, and which still captures most of the information in original data, right? So that's the idea. So there's no label involved here. You can think of that simple way. Yes, I mean, but sometimes we get, hey, I'm providing everything to the machine. The whole PCA or clustering, the whole algorithm is provided by us. How can it's unsupervised? So unsupervised is related to the data, treatment of data, not necessarily of the algorithm itself, right? So it's with the data, in respect to the data, right? I mean, there are efforts where machine has been asked to find out an optimum algorithm given a problem. That if research area is called neural architecture search or NAS, and still very rudimentary work. But that's the direction people are trying out, especially Google and all, who have tons of money to throw at these problems and not worry about a return. So that is going on, but we still, I mean, the algorithm part is still done by humans, right? All right. So, and that's what maybe that's one thing where our algorithms are not as good as brain, right? We want to build a brain basically, right? With all machine learning, deep learning, we are trying to build a brain, but brain is super good compared to any algorithm out there. And it may not be machine's problem, it could be our problem because we are building these algorithms, right? So let's look at math of PCA.
So I just wanted to understand that, so every time we have the numeric tables that we have in all our assignments, so would it always be good that we should be using PCA and all of that so that we remove all the...
Why not? Why try it out? Yes, there's no harm in it. Try it out.
Is there a problem that you, in numbers?
The only thing is if it's a non-linearly separable data, non-linear data, then yes, it may not do a good job, but yeah, if it's linearly separable, yes, why not go? Especially for the structured data, I would say go for it. I mean, why avoid using it?
And for linearly, it's like a rule that we, I mean, if it's non-linear, it's a rule that we shouldn't be using, or it's like for non-linear also?
We can, I mean, it will not give you good results. It will not give you good results. The reason just being because it's at its heart, it's linear math. That's the reason, right? So you'll not be sure whether the results are good or not. I mean, right? I mean, it might still give you an answer, PC1, PC2, PC3, but you're not sure whether they're really good or not, right? Okay, so what we are going to do is we are going to learn math, how to do it in math, all the rotation part, and SSDs and Eigen Value vectors. So we will do a simpler math, not do math over multi-dimension, because that will require multiple classes. So we'll do just a simple quadratic equations, right? So we'll start with a table with or a data with two dimensions, f1 and f2, and so of course we basically use metrics. So how do we draw metrics, by the way? I just want, I mean, this is nothing to do with the class, but if some of you are not sure how to draw metrics or visualize a metrics in your notebook, your Python notebook, sometimes you want to see draw metrics and show it to others, or so how you can do that? Sorry, simple data frame, is it? Okay, no, okay. Now, I mean, visualization perspective. So, what I was saying, that I struggled quite a bit to draw these brackets around the metrics. Okay, I struggled. I thought, I was drawing it with, but apparently there is a nice language called LaTeX, LaTeX, which you can actually write in your Jupyter notebook to draw these. So I just wanted to share because I struggle with it, and I want to make sure you know it so that you don't need to worry about how to draw. Earlier I was drawing one line here and then small line, another small line, and those buggers will never meeting each other. So that was a struggle, right? So, but now it came out nicely. So, I just thought I'll share. So this is a matrix, right? What is the size of this matrix? 6 by 2, right? 6 by 2 matrix, right? This is the data that we are working with. Now, the first thing we do is calculating the mean, right? We calculate the average of each feature, and I have made small change to our earlier example. Rather than 0.83 and all, I got nice 6 and 4, right? So I got 6 and 4, basically add all of them and divide by 6, right? And so this is my new, and once I knew how to draw matrix, I got crazy with it, right? So this is how we will shift the mean. Basically, subtract the average of that feature, and somebody pointed out earlier, which I have not corrected. Yes, there's error. This should be 6 here, right? So I have not corrected it. Basically, this is the new matrix that I will have. Right? This is where I need to rotate the line. Right? That's once I've done this, I will need to what this means in math, that we have shifted the origin. We have shifted the origin now. Right? So now, before we can calculate rotate the line and all, we will need to learn something about variance and covariance. What is variance? In a particular feature, how your data is spread out. Yeah, right? So how do you calculate it? Actual minus? Something like this? Right? Sorry? Yeah, this, okay, so there's a particular, I mean, this should usually square, right? But I have, there's a particular reason why I kept it this way. But yeah, right? So yes, I mean, so now this is variance. This tells me about how varied a particular feature is, right? What is covariance? Covariance basically tells how two features basically are related to each other. Like, how are they kind of moved together in one or not at all, right? So, and the formula is this, right? If x and y are two features, so you say actual x minus the average of x and multiplied by the difference, and divide by n minus 1. So we have to work with variance and covariance, right? Because that's what PCA is taking advantage of. It is taking advantage of variance and covariance, right? So we have to know the math behind it. Now, so this is the matrix that we have, and we can use matrix multiplication to get covariance. How many of you are aware that if you want to calculate the covariance, we can actually use matrix multiplication. And how do we do that? It's very simple. We just multiply the transpose of a matrix with itself. What is the transpose? Close to rows and rows to columns. So first, when we say our matrix is 6 by 2, and when I transpose it, what will be the dimension? 2 by 6. Then I multiply it by 6 by 2. So what will be the output? 2 by 2, right? I mean, and that's what I'm interested in, because I want to know what is the covariance between x and x. What is the covariance between x and x if x and y are two features? So this is basically nothing but the variance. That this will give me variance and this will give me covariance. Of course, it repeats it twice on for x and y. Y and x and y will be same, right? It doesn't make any difference, right? So it will repeat, but it's an easier way to calculate a covariance, right? So we can calculate a covariance. This is how we do it, right? And when we multiply, we will get something like this. We will get something like this, right? We just multiplied the shifted mean values with the transpose of itself to get the covariance in our data. Variance and covariance, right? So we will need to calculate this, right? So that's the first thing, or the second or third thing, right? We do, right? And then once we have the covariance matrix, then it becomes really simple. I'm just kidding. Okay, how do I get these values? I have to divide it by n minus 1. Remember that, right? I have to divide by n minus 1. N is 6 in our case. We have 6 examples. So divide by 5. That's the definition of covariance. So just the multiplication will give me the total, and I still have to divide it by the number of example minus 1. Right? So this is my covariance. Now I want basically what the idea is, how do I get PCs, is basically I can want to get eigen vector and eigen values of the covariance matrix. So covariance matrix is coming from our data, right? I mean, we have started with F1, F2 and we got it to covariance matrix. Now I want to calculate eigen vectors and eigen values of the covariance matrix, because covariance matrix is basically it has the variance and the covariance information which represents the information in the data, right? And I want to build these two things called eigenvector and eigenvalues of the covariance matrix. So how do I do that? So this is a simple equation. AE is equal to lambda E. A is equal to lambda, right? I mean, you know, that sounds so easy. I mean, but not in the matrix world, right? Not in the matrix world somehow. You know, so but these are, you know, that's what you know, that's the equation for eigen vectors. So what is A here? A is nothing but the covariance matrix that we have built. Now what is lambda? Lambda is the eigen value. Lambda is the eigen value, and E of course is eigen vector. Right? That's the property of eigen vector, is like when you multiply it with the matrix, it gives you the output is the eigenvector multiplied by the eigenvalue. And if you again multiply lambda E with E, you still get, you know, E and with lambda square, right? So that's the property of eigenvectors. Again, I mean, you know, some people have gone, I mean, who really understand this part. I mean, it was not meant for PCA. You know, somebody, you know, discovered it, or, you know, came up with it for some other reasons, but we just ended up using for PCA, right? So if you're interested, just go to YouTube and learn more about eigenvectors and their significance. But it's a little complex area, but if you're really interested, go for it, right? But here we are going to use it for math, right? So how do I solve this equation? So what all I have here? I have the covariance matrix, right? And the other two I need to solve, right? Other two I need to solve. So what I will do is basically convert this into a kind of a related or same equation, which AE is equal to lambda IE. What is I now? Identity matrix, right? I can use an identity matrix to carry out my work a little more easier. So of course we can move it to one side, right? Just like 7th or 8th grader do, right? And we can move it to one side and get 0, and then we can do this, right? And now, because so what should be 0 here? A minus lambda I has to be 0, right? Because E cannot be 0. I mean, if eigenvector is 0, what is the point of doing this, right? A minus lambda I has to be 0, right? This, so essentially in matrix, so to make this part 0, A minus lambda I, we can check whether the determinist value of A minus lambda I is equal to 0 or not. Now what is this deterministic value? You just multiply across and then come up with an answer, something like that. Like if it's, I think it's 5, 3, 4, 2. So you multiply 5 by 2, 4 by 3, right? And like that, and then that becomes your value. Is it plus or minus? I think it's plus, right? Okay, cool, man. So you know the person. You know the, I mean, all right, but thank you. So that's what we will do. We'll try to find out what is the deterministic value of this equation is. Now, in this case, I just need to find lambda, right? Because E is not there. There's only one variable I need to find out, and with one equation, it's not that difficult. Not that difficult. So suppose this is my this is my equation now. So I have my covariance matrix, right, which we calculated earlier, then minus lambda and identity matrix, right? So now we can have it as like this, right? And then this looks okay. Now we can calculate the deterministic value, and that's how it will look like, I guess. There should be minus, not plus, right? Right. So now we need to solve this equation, right? And it will come something like this, right? So what will be the value of lambda here? This is quadratic equation, simple, right? What should be the value of lambda here? How many values of lambdas we will get here? 2. Right. So because that matches with our number of PCs we want, PC1 and PC2. So how many? How do we get it?
A plus B.
No, I'm asking you to solve the equation.
All right. These are the values. I just cheated. I looked at the answer and then said, okay, because it had to add up, right? So it's 28.6 and 13.8. That's the values of lambdas. So we got 2 lambdas, right? Like 2 lambdas here, which means, so what does lambda represents here? These are the SSDs actually, like we talked about. So there's no rotation of line. That was, made up thing. And we can just do it through math using the quadratic equations, and we get lambda. Our SSDs are calculated without going into, all D1 square, D2 square, and D3 square. That is all done here, right? These are eigenvalues. Yes, these are eigenvalues because eigenvalues are scalars. Scalars like individual numbers. And eigenvector is anyway vector. It has to be, in that matrix, not matrix vector. I know we interchange. Vector is 1 dimension data, right? This is 0 dimension data. Scalar is 0 dimension data, right? So what does it tell us? These are eigenvalues, right? And in this case, it tells me the first eigenvalue captures. I don't care about the absolute values of lambdas. What I'm interested in is just percentage, right? I am interested whether it captures 50%, 30%. So here, if you add up all these both values and did 28 by this thing, then you will get 67%. So first lambda, the higher lambda captures the 67%. And the second one captures the 33% of the information, right? In our data, right? So now, we have eigenvalues. Now we need to calculate the eigenvector, right? So we will go back to this, and we can now plug in our values. Suppose E is x1 and x2. E is because we don't know what it will. We know that it will have 2 numbers because we are working with F1 and F2, 2 features. So even every eigenvector will be of 2 features. So this is the equation, and when we multiply it, when we replace lambda with 28.6 because that was the first one, and this is what we will get, and it says x1 x2 is equal to 1 and 1. Again, we can look at the deterministic point, right? So how it will go? How we will do it? 7.4 x2 minus 7.4 x1 and plus 7.4 x2 again is equal to 0. So this become minus 14.8 x1 plus 14.8 x1 is equal to 0. So this is x2. So if I move this through, anyway 14.8 is common. So minus x1 plus x2 is 0. So both has to be equal to get 0 answer, right? x1, x2 is equal to So you can say 1, 1, because we are going to look at unit vector. So we can say 1, 1. 1 satisfies this equation. Any value, but we are going to go with, yes, it can be 5 and 5, 10 and 10, 100 and 100. But remember, our eigenvectors are unit vectors. So we are going to keep first number as 1 and then go from there, right? Because we want a ratio, not the we are not interested in actual value, rather the ratio between our underlying features. So right. So now this is my, for the second one. Second one, it will be 1 and minus 1, right? 1 and minus 1. So now, so which one is my PC1? So I have now two PCs or 2 eigenvectors. Which one is PC1? 1 and 1, right? 1 and 1 is PC1 and 1 and minus 1 is PC2, right? So we got everything we wanted with simple math. It's not that difficult, right? 1 and 1 and 1 and minus 1. Yes, please. Okay, why we took covariance? Because in statistics, the variance actually captures in a way, because if your data is same, so let's not talk about variance and covariance. For example, if you have 2 features, both features is same number. X1 is 2, X2 is also 2, X1 is 3, X2 is 3. What it means that what we do, we use these data points or the features to differentiate between individual examples, right? If both numbers are coming same for each data point, then when we can say X2 is not really useful for me. I can just work with X1. Why care about X2? Because it's basically same as X1. So so basically we want to, and if your number is same, suppose all the values, now another example, suppose we have just one feature X, or like just consider one feature X1, and all the values in that feature for all the example is just number 5, right? So what it means is that that particular feature cannot be used to differentiate between example A and example C, right? It's both, for both cases it's just 5, right? There's no variation in the data. That means when there's no variation in the data, the variance will be very low, and when there is a lot of variation, then variation will be high, because we will have a mean value, and if the data points are far away from mean, then you will get a lot of variation, right? So that's the for example, if you talk about another example could be text information, right? Textual information. Now in text, have you heard of this term called stop words? Yes. Right? Everybody has heard of stop words, and we say remove stop words. Why do we remove stop words? Why doesn't it have significance? It is an English word. We use it. If it had no significance, why would we use it? They are common, actually. That's right. So what is there? Because every document has the A and all. We cannot use them to differentiate between these different documents. Same way here, if your data points are same, if variance is low, then you cannot use that data point to differentiate between your examples, right? And the covariances, like if the features are connected to each other, if features are connected to each other, that covariance will be high. Means that those 2 values are changing together. So rather than using 2 values, just use 1. So that's why we use variance and covariance to capture the information available in the data set.
So instead of covariance, we can use correlation also. I mean, just divided by variance, and we can go for that matrix also. Because correlation formula is covariance xy divided by variance of x, variance of y. So we can go for that also. That would be easy to calculate.
I don't know if it will be easy, but here what we want to capture is the variance information. We are more interested in capturing the variance information, because higher the variance, we want to capture higher variance. So we are directly capturing higher the value of the variance, better it is for me to basically come up with PC1s and PC2s. right? Why go to correlation then come back again? So you calculate covariance, go to correlation and then come back to variance, right? It will be a double. It's like that going from nonlinear to higher dimension and then coming back, right? So here we are directly capturing the variance and the covariance, right? Was simple math, not too difficult, right? Right? So now let's see how we can use PCA, right? PCA, I mean, we will look at few examples so to make sure we are comfortable in using it. So let's go back. I mean, we'll try that out. Okay, you will see it in a sequence of 1A, 1B, 1C. I made it really easy for you guys. Anyway, you'll get 5-6 files, and all the examples we do here, you will get all of those.
Yeah, it is.
Okay.
We just uploaded last time.
All right. Anyway, don't worry, you will get it. Okay, so we are going to look at Iris dataset, and I know all of you are tired of that dataset, right? I mean, it just keeps coming back. Okay, at least something new can be learned, right? So you guys learned about the metrics, right? Or at least I told you guys what to look for. So okay, so the reason I put this picture is because even I get tired of Iris, right? I mean at times. So I thought, let me see what Iris dataset means, right? So its Iris dataset apparently is about leaves or the flowers, leaves, and they talk about sepal and petal, length and width of these two. And so this picture shows you what a petal is and what is a sepal is. So at least some additional knowledge is gained by you. Now, how do I draw this? Is we can use something called markdown language. Is it, what is it? Markups. Is it markup? No, markdown only, right? So yes, so you can say you can essentially you can put a exclamation bar and then put the text in square brackets and then give the URL in the URL of the image in the so that's how it works. Okay. Okay. So thing to remember is markdown. So if you Google markdown Jupyter Notebook, you'll see all these examples. You just remember markdown or note down markdown. Okay. All right. So let's look at. We are going to load the Iris dataset. All right. Now that you know, so how many examples are there in this dataset? Is okay. By the way, is the font size okay, or should I need to increase it? Okay. Okay. How about now, or a little bigger? This is okay. This is okay. So how many data points we have? Only 150. Right. The advantage of using this dataset is like we can do this exercise in the class. Usually, otherwise, it might take hours to days, and when we go to deep learning, weeks and months. So I mean, that's why these datasets are useful. It at least allows us to learn things pretty fast, and so that we can try it on bigger datasets. Right? It's not about the dataset; it's about the concepts. Right? So feature names, basically, of course, we talked about sepal length and sepal width, and petal length and and target names. Of course, we have, I think, 3 types of flowers. I can't even pronounce them. All right. So we have 150 examples, each example having four data points, and so 4 dimension data. Right? Here, let's talk about dimensionality. 4 dimension data, and then sorry. So we have labels also. We have labels also here, right? And we said we don't want to deal with, in unsupervised learning, we don't deal with labels, right? We said that, right? That's what the basic definition is. So what we'll have to keep ourselves honest, we are not going to use labels while applying PCA, right? So just to make it a little more interesting, I'll try to draw it in 3 dimension. This is how the data set looks like. How the data set looks like in 3 dimension. We still have not been able to cover the 4th one, which we probably can cover with the size or something. But So okay, so that's a good thing. So so that's another learning along is basically you can use this library called, I guess is it available with, I think it's available within matplotlib itself, but so MPL toolkits.mplot3d module, and then you can use the XS3D, right? So it just looks a little more impressive than two-dimensional, right? So now let's go get to the PCA part. So we're going to build a decision tree classifier, and we do the train test split, and we just quickly train it, and score is 88.88. All right, again, this is without doing the PCA, right? We did not do the PCA, right? It's basically pure classification on all 4 dimensions, using all 4 dimensions. So now let's see if we can reduce number of dimensions and work through it. So PCA is available in scikit-learn decomposition module. So you will need to import PCA from there. And first of all, we just center our data, right? We calculate the mean, and we basically get the information. Then we basically fit it on the centered data, and I'm saying it n components is 2. What this n components 2 means that I want PCA to give me 2 components. From 4, converted it to 2 components. Now, of course, I'm doing this without even knowing what percentage is being captured by these 2. But this is just we will see how do we get about capturing all of them, and then deciding how many we want to keep. Here I've said, okay, from 4 I just want to keep 2. Can you give me only 2? So this returns me 2 PCAs. So I can actually now, this is a trained PCA, and now I can transform my input data, right? Input data was 4 dimension, and what I'm doing is I'm transferring, you can see this is my input data, X centered. If you look at X centered shape, 150 examples, but now only with 2 features, right? From 4 we got it down to 2, right? Now let's plot it out. Let's plot because we have 3 categories here, 3 type of flowers, but because we have only 2 features, we can easily plot them, right? Let's see if it may, without doing any classification. So we have not done any classification here, right? So let's see how the data looks. The 4-dimensional data even in 3x was hard to look at, but look at the data now. It clearly shows us that there are 3 type of flowers, right? If this one is setosa, green one is versicolor, and then this is Virginia or Virginica, right? But what you see is like your 4-dimension data has been brought it down to 2-dimension, right? And not only that, it gives you a very nice, it has captured the information that is there in 4-dimension into, even though it's just working with 2-dimension, right? We can see really that it works, right? We can visualize the data, and it captures the distinct features of underlying data, right? So you can see that, right? So now what we can try to do is, what are my Eigen Vectors, right? What are my Eigen Vectors? These are my Eigen Vectors. What does Eigen Vectors means? It's a unit, right? Unit vector. So the and what it showed, this is the weightage given to 1st dimension in the original data. This is the weightage given to the 2nd dimension in original data, 3rd dimension. So in this case, the highest weightage is given to the 3rd dimension for PC1, whatever that might be. That might be what was the 3rd dimension? Let's look at that. to petal length. So petal length is the most important feature that basically captures the good variance information, right? 0.85. No, okay. Yes, we have converted the actual data in 2 dimension. To convert actual data into 2 dimension, I will need PCs. Now, each PC is a linear combination of all the 4 original features. So it will have, remember, we had to calculate the ratio between F1 and F2. Here, this is a ratio between F1, F2, F3 and F4. Because we have 4. We are dealing with 4 data points now. 4 features, sorry, not the, right? Does it make sense or no? Right? So PCs will have 4 points, like as many features in your original data, right? But there are only 2 PCs. You can see that. First PC and then the second PC. This is the second PC, right? Because although there are 4 dimensions, I asked only for 2 PCs by saying n components is equal to 2, right? What is the explained variance? What is the explained variance is by these 2. PC1 captures 4.22 and PC2 is 0.24. What does this mean? It means nothing, right? Because these are relative numbers. What I'm interested in is the ratio. PC1 captures 92.4% of the variance in the data and PC2 captures 5.3. Together they capture 97.7% variance in the data. So which is pretty high, right? We threw two dimensions out, but we threw away only 2-3% information, which might be noise actually, right? So you can see how much variance is captured by whatever PCs we are keeping. It's the property is, or the attribute is explained variance ratio, right? Now we can try to build a decision tree again using the PCA features rather than using the original features. Just use 2 dimension. So we will do that, and so I'm just going to transform our input data using PCA and train it, and let's see what is the score. We got 91.1, which means we basically improved over 88.8 earlier to 91.1. So there is marginal increase, but still there is an increase, and moreover we are able to visualize our examples very nicely, right? So same thing we can do with more dimensions as well. This was just four dimensions, not a big data set, but the idea was to show that how it works, right? How we can use it to visualize our data, reduce the data, and still build. Because once you reduce the data, you want to do something with it. Either you can do clustering or you can do classification, regression, or something. You want to use it for something or just to visualize it.
For this, we don't need any domain knowledge.
For this, we don't need any domain knowledge, yes. Because it just goes with variance and covariance. Right? How would we justify increase in accuracies? We have thrown away some of the noise. We have reduced the correlated data. This is purely uncorrelated data we are working with, which means machine is better equipped to build a model.
Here we use this explained variance.
Yes.
We have considered only 2 principal components.
Yes.
Out of 4.
Out of 4.
And then we are taking the ratio out of it, and we are saying that 90.
No. Okay, no. It is not just out of 2. If it was 2, it must be 100% total. Right? It is out of all 4. Out of all 4, the first one captures 92.4 and second captures 5.3. Right? If it was all 4, it will be 100%, because how are we calculating? We are adding all the eigen values to say this is 100%. There's nothing outside of it. Right? So this is with respect to all 4 only. So that's why we said PC1 will always capture the highest amount of variance, because we have spent effort in rotating that line. Right? After that, it's slower and slower. Now we got 3 PCs. Explain, the next one basically gives me only, this one gives me 1.7%. The third PC captures 1.7%. So the remaining one, how much it will capture? Maybe 1.5 or 1. Something like that, right? And you can still build your decision, and it basically gave me the same answer, I guess. So the third PC actually did not make any difference. It was useless. Basically we did not need to use it, right? So this is how you can use PCA for dimensionality reduction, and then using that dimensionality reduced data for classification or clustering or anything you like, or visualization also. Third one is this one. This is the PC value above. How we built it. This is how we built it. Are you talking about the picture? Okay. I say n components 3. However components I want, I can get it. If I don't specify, it will get me all of them. And then I can say what components I want to use. Sorry? Notebook, okay. Yeah, that's my apologies and Edwin's apology. We couldn't bring, it was already there. I should have been uploaded. I think I was slow to share it. I think I will do it tonight itself. Don't worry. As soon as you go home, it should be there.
Why we are defining these 2, 3? I mean, we can just get all the 4 and then we can specify. Okay.
Yes. Why specify? Right? So sometime what happens? You say, okay. Sometimes you say, my machine can deal with only these many data points. This is how much memory is available to me. My machine learning algorithm, I can take only 5. So give me only 5. But that's a very rare case. Usually, we will see another example where we can get all of them, and we can see how much is the explain ratio by each of them, and then say, okay, this is my cutoff. I need 7. I need 3. Why I said 2 here is, again, just to show the functionality and quickly visualize the features.
How to decide about the cutoff? I mean, what logic will go with it?
Go on. Okay, guys, the question is, how do we decide what should be my cutoff for how much variance to keep in the PC world, right? How much? Usually there is no hard and fast rule. First of all, this is again based on judgment, and what people say that try to capture about 90%, if possible. Capture about 90%, and then you can leave out rest of it. So but here we said we are going to capture 3. When we say n components is equal to 3, we are saying we are going to capture, we want PC1, PC2 and PC3. Because there are total 4 PCs here. So the value of course has to be equal to less than 4.
Here if you look at that, there are 4 features.
Yes.
And these 4 features, it depends on the 4 flowers what we have.
Yes. No. Okay, what are the features? In our example, the features are sepal length, sepal width, petal length and petal width. And here, okay, that's a good question. What are these features? I mean, first of all, if you see, the PCA has no clue what the flower is, right? Whether it's Virginica or anything, it doesn't care. We have not fed that data. We have fed only the input features, not the dependent variable.
Sure.
Okay, so is that clear why PCA is unsupervised? We have not used our label to influence any of the outcome, right? Now, okay, let's come down. Let me know where you want to stop me.
So, come down, the bottom.
Bottom?
Yes.
All right.
So now, you're saying that the model score is 91%.
Score, yeah.
There is a classification what we have done.
Here we are doing classification. Here we are using the label.
So basically, what is the classification we have done over here?
We have done the classification against the flower type.
Flower types. So exactly actually, so that is what it was there before. So now I wanted to predict based on 2 or 3 PC components.
Yes.
So how do I get the input from the customer and therefore I can predict.
Okay, good. So how do I actually, so this was like, it was available to me. How would I, so customer is only going to give me sepal length, sepal width, petal length and petal width, right? How do I predict it from this decision tree classifier? So what I would do, I will get those inputs. I will say remove by, first of all, shift it by mean. Remember that first shift by, we have done the X centered, shift the mean, basically subtract the mean of those features. We know the mean. Then we will do a PCA dot transform. So we will have the PCA model. We will say PCA dot transform and feed those 4 values. And because we said we want only 3 values, PCA will convert these 4 values into 3 new features for PC1, PC2, PC3, and those 3 new features will get fed to the decision tree because it can take only 3, because that's how we have trained it, and then give the answer.
Great, actually, that's what I want to know.
Okay.
So,
I mean, that's a good question, yeah.
Can you please actually, so incorporate that code also and give it to us when you give?
Which one? Or the, okay, or you mean prediction code? Yes. Okay, I'll let, you guys are, okay, let's do it right away. So what we can do is model dot predict and what is that? PCA dot transform, and let's say X test is our input. I will just take first example of X test, right? That's it. And array, it says value of 2. That's it.
So it should be value of 3 now, because they have given a PC.
No, by value of
3, no? Number of components.
No, PCA. Okay, all right. So I have done everything in one line. So if you look at this line, what is happening? I take how much X text will have. X text, one example. How many values it will have? Not one example, but how many values that, or how many features that one example will have? 4, right? So what we do is on those 4, I do PCA transform, and what that PCA transform, that 4 gets converted into 3, and that 3 gets fed to this decision tree model, and then this 3 will give me the number with highest probability, and that happens to be 2.
Okay, so this is the value.
This is the final outcome. What flower it is? What flower it is?
And X test we have shifted mean, and that mean is from the training set, right?
Yes. Right? Yes.
When you were choosing to be n is equal to 3 in the P3, so you automatically choose the top 3
PCs.
Now this one
Here we are saying, here basically when we say PCA dot transform, that means PCA is already trained. It is trained to give me 3 top features, right? And what PCA dot transform will do, it will take the input of 4 features and calculate PC1, PC2 and PC3 value for that particular example and give me that. And I will feed that as an input to my.
Where would we got that data X train, Y train, X test, Y train?
Yes.
That's the input data.
That is the input data. Yes, that's the. Sorry.
Where have we got that?
Oh, this one we, okay, where did we get the data? We load in Iris data set. This one. Right? We first X and Y, and then we used split, train test split to get X train, X. Otherwise it will throw an error. At the bottom? That is basically one of these 3 values. I guess it will be Virginica, because 0, 1, 2, I think it will be 0, 1, 2. 2 means Virginica, I believe. I mean, you can check that out. Okay, yes, your question, please. To go to the bottom. All right, guys. Let's avoid chatter between ourselves or keep it minimum. So, all right, good. Yes.
0, 1. 0 is actually, so 0 row.
Okay, what does this 0 colon 1 means? Just the 0th example. If I can feed multiple examples for testing, for prediction, right? If I feed, say I say 0, 5, it will give me, it will take up the first 5 examples and do prediction on those. And it is telling me the First example is Virginica, second is the second one. And the third one, then first one, right? So yeah, all right, okay, guys, yes, everybody comfortable with it? How to use PCA, right? So all that math and everything is actually hidden behind this one line, right? So you know again, but the key thing will be to understand why to do PCA, right? Because you may not remember all the math and all, and you're not required to do the math. It's for understanding. But first thing is, important thing will be to understand what problem it is solving for us. As long as it's solving some problem, we will know next time how to use it, because it's just one line. It's a simple thing. It's a very simple thing, right? So, all right. So everybody okay with, or everybody basically convinced the utility of PCA? Yes, right? Okay, let's take another example. And this time what we will do, we will try to do the dimensionality reduction. All right, so that's another data set which you will be tired of, is digits. How many of you are familiar with digits data set? No? All right, good then. Sorry? Okay, so what is digits data set? It's handwritten digits. Okay, so I'm going to load it. And it has about 1800 examples. Each example has 64 features. What does we're saying that this is handwritten numbers. Is it what kind of data it is? Is it an image data, text data, or image data? So how many dimension image data is supposed to have? Pixel, image will have pixels, that we know. That is definitely there. Right? Each pixel will have some value usually between 0 and 255, right? That we know, right? But how many dimensions an image has? 2, 0, 1, 2, 3. It's hard to visualize because it's a very small picture, 8 by 8, right? I mean, our cameras captured like 2000 by 2000 pixel or something like that, right? Or very high resolution. This is 8 by 8. The reason is because they wanted to run it on machines built in 1995, right? So these can run for experimentation, right? So how many of you are familiar with MNIST dataset? MNIST. Okay, MNIST, M-N-I-S-T. So MNIST dataset is again a digits dataset, but it is 28 by 28 pixel pictures, 28 by 28. So it's easier to look at, and you can basically make out there's some number there. And it was basically released by this gentleman named Jan Lee Kuhn, maybe in late 90s. Are you familiar with the name Jan Lee Kuhn? No, okay, Jan Lee Kuhn is actually one of the top names in deep learning, and he leads Facebook AI research, in Facebook. So I mean, he's been working on this field for 30 years, 40 years maybe. He's grown old, so he was the one who, so if you want, you can actually use that data set to try out, because there you will be dealing with 784 features. Like 28 by 28 means 784 features, and try to reduce dimensions there, right? That will be really interesting thing to do, right? Here we are still dealing with 64 dimensions, which is still good, right? We want to bring it down. So let's see how we can reduce this 64 dimensions into lesser numbers and still capture information out of it, right? That will be a cool thing to do. 64 dimensions now. Earlier in Iris we had only 4. So it was, okay. I mean, not a big deal. But 64 to 2-3 will be really nice, right? So let's do that. So we basically again center it, and so I just trained, and I just said give me only 2 components out of 64. From 64 we are coming down to 2. How much our data is getting reduced? Sorry? How did we load the data? How did we load the data? Okay, so this particular data set is available in scikit-learn, which you can say, okay, I'm sorry I didn't go through that code because I thought.
No, actually, can we get an example of how to load the data if we have some data set?
Maybe let me think. I'll try to have this example tomorrow. Again, tomorrow morning we have another class So I will try to bring that.
Because that is where we can start. Otherwise, we can only actually.
All right, we will do that. So what we will do, we will basically try to see if we can load some data, and yes, because you're not going to work with only with this training these are called toy data sets, which are important for learning the concept, but it doesn't add value in terms of the data, right? This is like all right. So let's go back and okay. So we have done the PCA, and we are just getting 2 features now out of 64. From 64, we are bringing it down to 2. So let's transform it and shape just to confirm that it is only 2, right? So 1797 examples and only 2 dimensions for each one. And all right, now let's plot it, because now that we have the data in 2 dimension, I can have a 2D graph of the whole 10, right? So I'm going to display all the 10 numbers, and in, let me say F11 and toggle header, like, okay, I thought, okay, so this is the 2-dimension representation of our 64-dimensional data, right? So 0 is all black, this is all zeros, but you can see it still got a lot of zero. I mean, it got variance in the data captured very well, from 64 dimensions only to 2 pixels now, or 2 features now. Imagine that. Right? It still got it very nicely. I mean, you can see, yellow is here, blue is here, purple is here. Very distinguishable. Very, very distinguishable. Right? From 64 pixels, so 64 values down to only 2 values. We have reduced our data by almost 98%. If we had 2 GB of data, we have gone down to almost how much? 4 MB. No, 40 MB, sorry. 40 MB. That's what we are saying. That's what it means. Right? That's what it means, that you reduce your data and still able to capture very good information about the data set.